Hi, folks. Can y'all hear me? Hello, hello. Okay. All right. What can I do for you? All right. Corey on Twitch had a question about how to set up number 6 on the homework. Okay. Anybody else have any topics or questions? Let me find number 6. A work problem and a collision problem. Okie dokie. Let's see. At some point, you can be here the whole time. Okay. Let me turn on my screen share. Okay. Huh. That's weird. It's not open anywhere else. But whatever. It can be read only. The hardest possible problem we may see on the test. Ooh. That's a hard one. How can this be locked by editing? And there is no other user. It's weird. Okay, number 6 is a pendulum. So I gotta think about the hardest possible problem. I'll have to think about that. Yeah. So for number 6, the pendulum. So the key here is that you have pendulum. So you have a dot, right? You have some place where it's attached. You have a string, and you have a bob, right? You can pull the pendulum back to some. It's actually like an amplitude, some angle theta, and then release it, and it will swing down, and then swing out, and then swing down, and then swing out, swing down, swing out, right? So the way to interpret pendulum problems, the easiest way is energy, because when you pull it back here, what you are doing is giving it, we're going to say this is my y equals 0. And then you are giving it some amount of potential energy due to that height, right? And then as it swings down, its potential energy will decrease and its kinetic energy will increase. So you have kinetic energy is 0 out here, kinetic energy is maximum down here, and then same thing as it goes out this way. So the equation for pendulums is, I believe, on your formula sheet, but you have to realize that it's only for pendulums. I've seen students try to use it in all kinds of strange ways. So if this is your starting point and this is the lowest point, and you start by pulling it to some angle theta, and this is, this height, h, we want to make that related to theta. So what we do is we make a right triangle where this is L, is the length of the string, and this is L also, right? Because the string length stays the same all the time. But now that we have a right triangle, this side would be L sine theta, and this side would be L cosine theta, but it's only part of it. It's not the whole thing, right? This part, right, just this part would be L cosine theta. So H is this, right? So you have a piece that's H, you have a piece that is L cosine theta, and together they add up to be L. So you can say, okay, L equals H plus L cosine theta, H equals L minus L cosine theta. I can pull L out. Is H. And so U is MGH, U is MGL 1 minus cosine theta. So that's where the equation comes from. And then the question is sort of how do you use it? Is you have at some angle theta, you have U is MGL 1 minus cosine theta, and then our kinetic energy is 0. At the bottom, our potential energy is 0. Our kinetic energy is 1/2 mv squared, which is equal to what I lost from my potential energy. So if you know theta, you can get the max speed, which happens at the bottom. If you know the speed, you can get the angle theta by doing it the other way. Now, where problem 6 gets a little exciting is that it combines a collision at the bottom. So you have, you can do, there's one type which is like a ballistic pendulum, where, for example, you shoot, I think problem 6 might be kind of like this. Yeah, you shoot a bullet at it. So you have a bullet that is being shot at this. So you have a momentum conservation, right? And this is one where they stick together. So it would be your M1 V1 plus M2 V2 equals M1 plus M2 V final. And this is one-dimensional, so we only need to worry about the x direction. One dimension. So then what you end up with is the bullet is embedded and the whole system is now moving at VF. Then it becomes an energy problem where you have 1/2 m VF squared, and that is getting turned into MGL 1 minus cosine theta. Does that make sense? So the momentum process is how you find V, and then once you know V, you can get theta. And then the same is true when it swings back down. So like you can alternately, like part 2 is you have a pendulum swinging down and it's going to strike an object. So you do the opposite. You do energy first to get V at the bottom, and then that goes into your collision equation. So it's the same kind of idea, but backwards. Corey, did that help over on Twitch? And I'll talk about collisions for a little bit, because that's something that I think students have generally been struggling with. Okay, the extra credit for test 1 is not in yet, I don't think. I have to check. Yeah. My weekend is going to be a lot of grading. Collisions. Okay. I have not forgotten, but it has not gone in yet. There was a question on exam 3 that described centrifugal force. Since it is a pseudo force, should it be considered as such? Yes. That was an issue on exam 3. There was that question that was like, what is the force that keeps there's an upward force on the thing in the bucket. It is not a real force. It's a fake force. A real force has to be something pushing it, right? What's the thing that's pushing the water in the bucket? Nothing. There's no, right? So the only real forces are gravity pulling the water down, the normal force of the bucket holding it in, and that's kind of it. So it's its own inertia that keeps it from falling out of the bucket. But everybody got that one wrong, which makes me think I didn't explain it very well. Yeah. So yes, it is a pseudo force. Do not ever put centrifugal force on a free body diagram. No centrifugal force on a free body diagram. And centripetal force is not its own thing. Trying to think of a good way to phrase this. So you do your regular forces, right? So tension, normal, gravity, friction, and then identify one as the centripetal. You're not going to add a separate one. So this is something that a lot of students have trouble with. Like you have something being spun around on a string. I did one of these yesterday. Right, this was the question from exam 3. That the only forces on this person being swung around in a circle was tension and gravity. There was no centrifugal force. There was no special centripetal force. Right, the x component of the tension was your centripetal force. But it wasn't its own separate thing. Yeah. Okay. All right, let's have a look at collisions. When is an interaction a collision? It needs to be more than one object, either start or end, or both, with more than one object. One object cannot be in a collision, right? And it has to fulfill sort of certain requirements, right? So needs to be needs to be an isolated system, which means there's sort of hard to really describe, because sometimes it's like, well, it's things like the example I think of is like a cannon. If you have a cannon that is like on wheels and it exactly what cannons look like, it's going to roll backward, right? Are there other forces on it? Yeah, there's probably some friction, right? But friction doesn't matter because it's so slow. So this would be considered an isolated system. But if your cannon was like tied down, is that an isolated system? No, because it has other forces interfering, right? Does that make sense? Right, so you can ignore friction, but you can't really ignore anything else. If it's like tied down, it's a problem. And the other rule is it has to be either needs to be short duration. So this means like if you have two blocks that are attached with a rope and they're sliding on a ramp or something, that is not a collision, because it's a long time. It's like they're attached the whole time. They're always interacting, as opposed to two boxes collide and then bounce off. They're only in contact for a very short period of time. Now, the one exception here is if they stick together or explode, right? So this means there's a change in the number of objects. Because like, for example, this pendulum, well, the bullet's stuck in the block. That's not short duration, that's long duration. They're literally stuck together. That's the exception, is that you have to do collisions. Okay, so this all hopefully makes sense. So you see a problem and you say, okay, is there more than one object? Yes. Okay, are they interacting over a long period of time? No. Are there any outside forces? No. Okay, I know I'm doing a collision problem. Okay, so the next question is, what kind of collision? And there are certain key factors. So things you should look at in the problem. Is there some change in the number of objects? That's important information. Does it say the words inelastic or elastic? And is this one-dimensional, two-dimensional, three-dimensional, four-dimensional, five-dimensional? 1, 2. Really, 1 and 2 are the only ones you're going to encounter in this class. 3 is too hard. 1D or 2D. Okay, what does 1D or 2D mean? Right, 1D or 2D is, do I have two cars that are colliding along one axis, or do I have two like billiard balls that are colliding and bouncing off in like a plane, right? So, all right, making sense so far? Doing good? You're also looking for words like stick together. That's another good one. If a problem says stick together, what does that mean? Now is the time for your participation. Yeah, it means it is an inelastic collision. It means they have the same V final. Okay. Now, collisions include two things, momentum and energy. Do we know anything about the momentum? And do we know anything about the kinetic energy? Yep, same final velocity, good. Momentum is conserved, yep. What about kinetic energy? Not conserved. In fact, it's going to lose its the maximum amount, which you're not usually going to use this fact, but it's kind of good to know. So what equation are you going to use? You're probably going to use momentum conservation. So m1 v1 plus m2 v2 initial equals m1 v final plus, oops, and these stick together. So it's m1 plus m2 v final. And then this is the one-dimensional. If it's two-dimensional, you would have m1 v1x plus m1 v2x, etc., and m1 v1y plus m1 v2y, etc. Same equation, you just need two of them. Okay. Hopefully that's making some sense. Okay. What if they don't stick together? Oh, there's also like a subset here. It's also a thing explodes or breaks apart. Right? So there's like a cannonball or a rocket. A rocket breaks apart. I think there was a question like this on a homework at some point. At some height. Right. Okay, rocket explodes or breaks apart. This is still inelastic because it is still a change in the number of objects. And all these same rules apply. You would still do momentum conservation. It's just now it would be m1 plus m2 v initial equals m1 v1 final plus m2 v2 final. Same idea. So if you're changing the number of objects, you're going to be doing this. From one object into three, or from three objects into one. Okay. What if the question says, usually it'll be something like bounces off in a perfectly elastic, or that you can assume it's perfectly elastic collision. Right. So what does it mean to have a perfectly elastic collision? What answers go here? Both are conserved, yes. Okay. So, there are some different things that you might see for this. So there's one-dimensional and there's two-dimensional. So one-dimensional, the thing here is the student's like, okay, I know I need to use momentum conservation. Okay, so I do this. Initial and final. Okay, and I know the same is true for momentum. Or, I mean, kinetic energy. Did I say momentum? And then there are two things that happen. Students either get stuck or they end up in a horrible tangle of algebra. The thing to remember is that the solution is on the formula sheet. Right, can I pull up the formula sheet? No, I had it in here somewhere. Oh, that's nice. Thanks, lawn guys. Glad to know that's essential. Where's the formula? There it is. No, that's the old one. No, that's fine. That is the old one. Physics 2 is the one that had a new one. Okay. Look at all these beautiful equations. Ideally, you should know what every single one of these is for and when to use them. If you don't, I advise you doing that before the test. What's with that? That's like out of place. That's weird. Huh. Well, good to know this isn't the version that you're going to have. Okay, it is these. They're not labeled, so you need to recognize them. These are the solutions to these equations, elastic collisions. So literally all you do from there is plug stuff in. Mm-hmm. So these are actually a lot easier. You're like, oh, I just use this equation and I plug things in. The only things to be careful of is to watch which ones you assign as 1 and 2. It's really easy to get like, okay, wait, which one was 1 and which one was 2, and then plug in the wrong number somewhere, or to mess up your signs. Because remember, signs matter for momentum, plus and minus. If you have two things coming in like this with equal momenta, their total momentum is 0 because signs matter. Okay. Questions about this? You might have a case where it doesn't say it's the lawnmower guy rammed into the light post, and now the light post is like wah 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 wah. It's pretty funny. Calculate the period of oscillation in the light post after it's been rammed by a lawnmower. So you might have something like this where it doesn't say it's elastic, but it does say bounces off. Usually it will give you some other information. You can't solve it if they don't give you some other information. So they might give you some information about the angle or the V final for one of the objects or something like that. Some extra piece of info. And then you know that momentum is always conserved. So you can do your M1V1 problem. Even if you don't know if it's elastic or not, you can always do this. You might not be able to do the kinetic energy one, but you can always do this one. Okay. How's this going? Is this making some sense? Helpful? Give me a emoji or an emote in the chat. This is helpful, or if you have more questions. Okay. 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 Yeah, you have one before physics, don't you? You're welcome, Dawson. If you have any questions about anything, like if you get out of your other final early, let me know. Okay. How about on Twitch? Everybody okay over on Twitch? Hopefully. All right, I want to look at something really quickly. And what do you want to talk about next? Work. Work sounds good. Give me a second to check something, and then we'll talk about work. So stand by. I need like a little hold screen. that plays like Girl from Ipanema. So I want to make one note about two-dimensional elastic collisions. If you see a 2D elastic collision, generally a better idea is to do momentum, not kinetic energy. Usually you don't have enough information. Usually we'll give you more information. It'll end up being something like this. If you try to do this equation, the 2m1, etc., from the formula sheet, it won't work because kinetic energy doesn't have a direction. Right? You can't do x and y for this because the kinetic energy isn't conserved in the x direction, it's conserved overall. So do momentum. Do momentum in every case except a two-dimensional or a one-dimensional perfectly elastic collision. Okay, and the other thing is sometimes in 2D problems, it will give you an angle. There was one like this on test 3. The thing to remember is that you can break it into X and Y components. So instead of having two unknowns, now you really only have one unknown, right? Because you know theta, you just don't know V. Okay. All right. All right, Shannon, I want to talk about work. Any particular aspect of work? Just sort of work in general. So while Shannon's thinking, I want to emphasize Physics 1 has 3 paradigms for solving problems, right? It has number 1, the first one you learn, Newton's second law. Force, net force equals ma. Number 2 is the momentum paradigm, right? This is J equals delta P and includes momentum conservation and stuff like that. This is just an application of Newton's third law. It's just a different way to do the math, right? It's not that one of these doesn't apply or that it's wrong. It's that they're useful for different situations, right? And then number 3 is work and energy, where work is delta K. So these 3, oh, that's not very good color. You're sort of asking yourself, which of these is more useful? And this is work net. This is JNet. So it's always about which of these models is the most useful. So for long-term stuff, So if you have like very short things like collisions or collisions, you'd want to do number 2. It's momentum. If you have things like static equilibrium, things like hanging from ropes and being pulled along the ground and things like that, you might want to use number 1. And number 1's useful for a lot of cases. Hang on, I'm having internet problem. Okay. Twitch has a nice little like green, yellow, red. So if it goes red, I'm like, and then you have your work and kinetic energy is useful almost everywhere number 1 is, right? Almost any question where you can do, okay, here's a bunch of forces, I'm going to find F net, and then I'm going to get MA, and then I'm going to do kinematics to do V final is V initial plus 2A delta X, right? I could just as easily do the same problem, but do the work done by each force is force times distance times cosine theta, right, for each of these. And then get the net work and set that equal to KE and get V final, right? So you can use these two almost interchangeably. It's actually kind of a problem for teaching work and energy because you can almost always just be like, okay, forget it. I'm just going to do F equals MA and get the right answer. There are certain places where it is more useful. Number 3 is better when some certain cases. So when the force is not constant, generally. So this is things like springs or things like wobbly hills as opposed to ramps, right? So for example, if you have somebody, there's a problem I think in one of the homeworks where somebody's skiing down some hill. Okay, hill's 15 degrees. Here's the guy. Here's his skis. There was other forces and stuff going on at the same time. So you could wobbly hills. You could do this either way. You could do work done by, well, you do his free body diagram. He's got gravity. He's got normal. It's for sure there's friction. So you would do, okay, we do our tilted axis. So the net force is going to be mg sine theta minus your force of friction, which is minus mu naught times the normal force. And our normal force is the horizontal or the vertical component of gravity, mu mg cosine theta. And then you get A, and then you do all your kinematics. Okay. You can also do, okay, the work done by the normal force is 0, the work done by gravity, and the work done by friction. This would be your force of friction times the distance of the slope. This would be your change in, it would be mgh. Really, you have to be careful. This is a negative mg delta y, but your delta y is negative, so you get a positive number. Okay. Hopefully this makes sense, right? These are the two approaches. And you should get the same answer each way. This is something you can do to check yourself on an exam, is do it both ways and see if you get the right answer. Like, I mean, obviously this presumes you have a ton of extra time, but yeah. Where it becomes challenging is if you have a hill like this, right? Okay, well, the guy's right here. So let's say there's no friction, because this gets complicated if there's friction, right? The force of gravity is, so our net force is just mg sine theta, but theta is always changing. So how do you handle that, right? Theta is 0 here, but then it's like, I don't know, 45 these places. It's different all the time. So this is where the fact that these conservative forces, negative change in potential energy, GH or negative mg delta y, you can do this. You can't do this, right? So generally, instead of doing F net equals MA, this is like, okay, I added up all my forces. A. Instead, you're doing adding up all of the work, and that gets you the change in your kinetic energy. And this is the most straightforward way to do it. There's also like the bar charts where you can call work done by gravity negative delta U. You can call the work done by friction delta E thermal. You can call work external, right? You can rename stuff, but this is the general idea. And you don't really need to worry about other stuff. Is that making some sense? Did you see doing that problem from exam 3 I did yesterday? That was right. This one with the the block on a hill and it slides down, all this kind of stuff. This one you do need to use work and energy because it has this weird little ramp, right? It's not a perfectly straight ramp. Theta is changing. So you do have to do work done by gravity is mgh, or negative mg delta y, and our delta y is negative. So that kind of tells us I've got to use work and energy for this. And then I think about what is doing the work on this thing. So it starts at 0. I have something doing this much work, and then I have gravity doing this much work, and then I have friction doing some negative work. And if I add all of those up from the very beginning to the very end, my delta K is 0. So I know that all of that work has to add up to 0. So we have near push, give 0.68 joules, down ramp, and then friction. So K initial equals 0. Then you have work done by the push is 0.68. You have the work done by gravity is, we don't know. You have the work done by friction is, you can work it out, mu K, mg, distance, -1. And you know that your Kf is also 0. So work push plus work gravity plus work friction equals 0 minus 0. You know this, solve for that. So thumbs up, thumbs down. You like it, you don't like it. Is it helpful? I could try to find a work problem to do. Okay. Sorry, I'm like rescheduling a meeting that was supposed to be at noon. Okay. Question 12. Question 12 from anything in particular? From the homework? Presuming this is the homework. So Shannon asked about the hardest problems. I would say to look at the torque questions on the homework because that's new. It involves a lot of new things like the combination of rotational kinetic energy and normal kinetic energy and potential energy and some really like, because it's new and you haven't seen it before, I would say reviewing these is probably like your best bet. Okay, for 12, you got a very different answer every time you tried it. Okay, tell me, what did you do? So you tried it several times. Tell me some of the things you did to try it. So you have a 1 kilogram ball and a 2 kilogram ball connected by a rigid massless rod. Massless means we don't care about it in terms of moment of inertia or center of mass or anything like that. So that's good. Rod is rotating clockwise about its geometric center at 17 RPM. What is the initial rotational kinetic energy of the system? What force should be applied to bring the structure to a stop in 4.4 seconds if the force can only be applied at a location 0.25 meters from the geometric center? Okay. So I talked about this like 3-step tactic yesterday. So 3 steps. Step 1, use brain. What I mean by this is read the problem. Make sure that you understand it. Imagine it. Make sure that you can picture what's going on, right? That your mental picture is correct. And also ask yourself sort of what if, why questions and look for red herrings. Second is to draw either a picture, a free body diagram, or both. And then to sort of to categorize, to think about what kind of question this is. What are the relevant topics? What are relevant equations? What are relevant like theories? What are some knowns that are not given in the problem, but you're supposed to know, like I'm supposed to know that momentum is conserved, or I'm supposed to know that the torque will all equal 0, things like that. So really, okay, let's have a look back at this problem. Okay, so we have 2 balls. They're connected by a rod, and the rod is rotating clockwise, clocks go that way, about its geometric center at a certain rate. Okay, It asks for the rotational kinetic energy, and then you bring it to a stop. Okay. So one thing I do as part of this is think about what numbers are they giving me and why those numbers matter. So I'm also going to draw a picture. It's pretty easy. Okay, so this is total of 1.1 meters, 1 kilogram ball here, 2 kilogram ball here. Okay, so the numbers they gave me 1 kilogram, 2 kilogram. They gave me the length of the rod. They gave me, it's rotating at 17 RPM. They gave me to bring it to a stop in 4.4 seconds. And they told me the force has to be applied 0.25 meters from the geometric center. So I think it's useful to ask yourself, do these matter? And if they matter, you have to make sure you're using them when you do the solution. If they don't matter, then you can just throw them out. Okay, so if I have a different mass on either end, will that affect anything about this problem, like the physical situation? So the answer should be yes. If they're heavier, right, that makes a very different amount of kinetic energy in your system. It means there's a different center of mass if they're different, right? It means that there is it'll take a different amount of force to bring it to a stop. So yeah, these matter. Does the length of the rod matter? Well, yeah, you're going to have a different kinetic energy if it has a huge moment of inertia versus if it has a really small moment of inertia. So yeah, that matters. It's going to have more kinetic energy if it's rotating faster. It's going to take more force to stop it. If you try to stop it quicker, you're going to have to take more force. And if you can apply the force at a different location, right, it's easier to slow something down. You get more torque if you're pushing at the end versus pushing at the middle. So that's going to matter. So whatever we do, we have to use all of this information. Okay. And then there's no red herrings. No red herrings. Hopefully everybody knows what a red herring is. I just realized that's very socio-cultural. Okay, then we think about categorize. What kind of problem is this? Well, that's pretty clearly a torque and rotation chapter 12 type question. Okay, so some of the equations that are relevant are torque equations, moment of inertia equations, torque equals RF sine theta, torque equals what am I talking about? I alpha, right? Kinetic energy is 1/2 I omega squared, right? So tell me what to do next. Yeah, I know that. Okay, Michael says find moment of inertia. Sounds like a good plan. How do I find moment of inertia? So I have two objects that are a distance r away from my axis. So I'm going to use my incredibly basic moment of inertia equation that's hidden under this blob, this one. mr squared. So my moment of inertia is going to be m1 r1 squared plus m2 r2 squared. Free body diagram. You can do a free body diagram. I would do that for our next bit, but you have to be careful because now you have to draw the whole thing. Say, okay, the force is being applied at a location 0.25 meters from the geometric center. So I have a force being applied right here, and it's rotating, it's rotating clockwise. So my force would be applied the other way to try to stop it. Because it has a fixed axle, it doesn't matter which side we're pushing on. So for this, we don't really have any other forces. It doesn't really tell us whether it's rotating vertically or horizontally. I think we can presume, because it doesn't give us any initial information about, the heights and things, that it's rotating like in a horizontal kind of situation. So the only force we care about is this one that we're going to apply in part B. Okay, excuse me. So our moment of inertia, 1 kilogram times r, which is the distance from the center. So if it's 1.1 meters long, then it's going to be 0.55, is that right? 0.55 meters squared. And then this is going to be 2 kilograms times 0.55 meters squared. So we end up with 3 times 0.55 meters squared. .55 times 0.55 times 3 is 0.9075 kilogram meters squared. Okay. Great. How does that help us? Kinetic energy equation. Yep. Gonna use this one. 1/2 I omega squared. 1/2 I omega squared. What do I do for omega? I'll make this I for now. Good. So we do have omega. Omega is our 17 RPM, but you always want to put it into radians per second. So 17 revolutions per minute is equal times 1 minute, 60 seconds times 2 pi radians in 1 revolution. So I get 2 times pi times 17 or 60, 1.78 radians per second. And that's what I put in here. So what will I end up with? Let's see. I have this squared times 0.9075 times 0.5. So I get 1.44 kilogram meters squared, radians squared per second squared, right? Radians disappears, it's not a real unit. Meters squared per second squared, that's the same thing as a Newton meter, which is the same thing as joule. I got energy, good. Hopefully that's the right answer. That nerd Chris, who I'm not sure who that is, because I don't, is that Christian? I'm trying to think, I think this is the only person named Chris in the class. So yes, okay. All right, so that's our answer for part A. Part B, what force should be applied to bring it to a stop in 4.4 seconds if the force can only be applied at that location? Okay, mentally what's happening? We have this thing, it's spinning, we want to bring it to a stop. We need to use the remaining parts of the information that we have not used so far. So, okay, why would the force have anything to do with how long it takes to stop? What equation makes that connection? Right, so we made our mental connection. Well, obviously, we need more force to make it stop faster. What equation is that? No thoughts? Okay, well, if we're talking about the force that it takes to make something stop, if this were a regular thing, it would be F equals ma, right? The equivalent for a torque problem is torque equals I alpha. Does that help? Right. The torque is RF sine theta. I, we already know. What's alpha? Have I lost connection? Nobody's participating. Makes me sad. Okay. Maybe I have lost connection. Oh. So alpha is our change in omega, delta omega over delta t. And I know that. I know I want it to go. I have to be careful here. So omega is clockwise. Clockwise is negative. So my alpha is going to be positive. It doesn't make a huge difference. Yeah. Very careful, Michael. That equation, it's not a t, it's a delta theta. You've mixed two equations. You want this one, doesn't have the squareds in it. So we have negative 1.78 radians per second. We want it to slow to a stop. So we get, gotta be careful. You'd get a lot of partial credit, but you might also lose a lot of partial credit because it's like you can't even copy an equation off the formula sheet. 0.4045 radians per second squared. Why did I use radians? Because I need radians for this equation. So R let's do this by torque, is going to be my I kilogram meter squared times my alpha, radians per second squared, and I end up with 0.367 kilogram meters squared per second squared, which is a Newton second, not a joule. Got to be careful, right? And then that is equal to not a Newton second, a Newton meter. Okay, good. Well, all right, everything's fine. Just drop my phone/calculator. So then I know that torque is RF sine theta. We can presume that sine theta is 1. It doesn't specify that it's perpendicular, but perpendicular gives you the best result. So it is fair to presume that you're doing that. Newton meters. Okay, R, what's R? .25. It is the distance from the axle to where the force is being applied. So it's not the 1.1, it's not something else. It's that 1.47 newtons. Hopefully that's the right answer. Did I use everything I thought I was going to use? Yeah, I did. And I didn't need anything that I didn't have. So, does it make sense? Yeah, I think so. It doesn't have a huge amount of kinetic energy. It's not going all that fast. So, a little bit of force brings it to a stop. All right. Thumbs up, doing good. Any more questions about anything? It's 12:20. I planned to go until 1, but if you have run out of questions and you just want to go study on your own, that's totally cool. I will be checking my email kind of obsessively until the exam starts. But I'm also happy to stick around until 1. So. (15B). Okay. So you asked about 15B. Can I presume that you got 15A? So we have a 2.6 meter long, 300 kilogram steel uniform beam that extends horizontally from where it's bolted to the framework, right? So it's very much like out, sort of dangling a lot of weight on that bolt with a construction worker standing at the end of the beam. Okay, so you got your torque due to the worker's weight. So how did you do that? What you probably did, you got A and B. I was going to say, how can you get A and not B? Okay. So you got, colors because I feel like it. You have a wall, you have a beam that has and a guy standing at the end. It was 2.6 meters long, 300 kilograms and 75 kilograms, 300 kilograms and 75 kilograms. Okay, you're given 6 meters long. You want to attach a rope at 2.3 meters from the bolted end. And it's pulling straight up, I think it says, right? Yeah. straight up. Okay. And we want to know the force in the rope. So we want to take all of these and get force rope, or the tension in the rope. Okay. So do we think all of these numbers will affect what result we get? I think yes. I think if we have a heavier beam, we'd need more force. I think if we had a heavier worker, we'd need more force. I think if we had a longer beam, we'd need more force. I think if we put the rope closer to the end, we'd need less force. And I think if we changed the angle, we'd need more force. Okay, so I don't see any red herrings in this problem. I've drawn a picture. We want to categorize it. What type of problem is this? Because this is the key here, is if you identify the type of problem, there is some hidden knowns that will help you. Okay, torque, can you be more specific? Part A and B were about torque. It was what was the torque by this way? What was the torque by this way? Part C is a little more complicated. There's actually a name for this type of problem. Nobody quite knows, huh? So I will tell you, it is a static equilibrium problem. Yeah, you find the torque on each side of the rope and solve for the extra force to make it even close. You're on the right track. The key here is that your net force has to be equal 0, and your net torque has to equal 0, and your torque is measured around the axis. So we have a bunch of forces. We have the weight of the beam. We have the weight, it's a lot bigger. We have the weight of the worker. We have the force of the rope. We also have some unknown force at this bolted end. We don't actually know what's going on there. It'll probably have a horizontal and vertical component, right? So it keeps it from swinging in and it keeps it from sliding down. But the torque, so we will have a torque from the bolt, a torque from the beam, a torque from the worker, and a torque from the rope. And we need to know that these all have to add up to 0. The torque from the bolt, RF sine theta, our R is 0. So this is 0. So we don't actually care what that force is. We could find it if we wanted to, but we don't care. So we already got a torque for the beam. I forget what it is. So this would be the weight of the beam times the distance, which is half its length. Torque for the worker would be the worker's weight, and he's standing at the end, and both of those are at 90 degrees. And they are technically both negative because they're both trying to make it go clockwise. In terms of how I drew it, it doesn't matter even a tiny bit in this problem. So that means our torque from the rope has to cancel those out. So torque rope equals mg 2.6 over 2 plus m2 worker g 2.6. Right? And the torque from the rope is going to be the tension in the rope times its distance from the axis times, in this case again, it would be sine of 90 degrees, equals 300, 9.8, 1.3. How much did the worker weigh? 75. 75, 9.8, 2.6. And I can solve for tension. Did I use everything that I expected to use? I did. Yeah. So Ben, this is probably close to what you tried, but it sounds like you used the rope as the balance point, but you got to use the bolted end as the axis. If you try to balance it around the location of the rope, I don't think you can, because the rope would be exerting no torque, and it would be like, well, beam is heavier, so it goes. So. Any other questions? I think that's what I found. Wasn't that right? Let's see. We'll do some math here. 300, 3. $24.92. Is that not the right answer? I get the right answer. Woo! Circular motion review. Sure. Circular motion. So circular motion. It's all about units. That's my summary. Students tend to get lost in terms of the numbers and like whether this is omega or alpha or t or what. But you should immediately be able to tell, right? So we have some problem and you pick out the following numbers. Okay. Tell me what variable, like name and symbol, goes with each of these. 30 meters is a little hard. This could be, I'll help you with this one. It could be the radius. It could also be like the distance traveled, right? Like you're driving your car around in a circle, or you're ice skating around in a circle, you ice skated 30 meters, right? It could be either of those. Okay. Shannon says velocity / speed. What kind of velocity? Linear. Linear, aka tangential. Both correct. Yep. Okay. Rotational. Okay. What is the... Okay. So both of you are giving me half of it. Rotational, angular. What is rotational or angular what? Okay. It's a velocity. It is a rotational or an angular velocity. Okay, good. What about the last one? Oh, and I'll add another one for you. Okay. Rotational or angular acceleration. Okay. Ooh, and I thought of another one. $302. What's that? Yes, period. The amount of time it takes to go around once. Right? No, it's a time. So it's the time to go around once usually. Or it could also be delta t, like over the next 302 seconds, it slows to a stop. So you have to be careful about which is which. What about the 25 meters per second squared? Is it acceleration? Yep. There are two possibilities for this one. Could be linear, could be tangential. These are the same thing. Could also be, what's another possibility? Centripetal, yes. So in terms of what variables, this could be r, this could also be delta x. This is probably vt or just v. This one is omega. What's the next one? Angular acceleration is alpha, good. Okay, this one could be delta t or it could be period. What's the symbol for period? T, capital T, good. And then this could be tangential acceleration. It could also be centripetal acceleration, which is also written on your formula sheet as AR for radial acceleration. Both all correct. Okay. So the first big step is identifying what you have and making sure you know what these are, right? This is the biggest difference that I see students get mixed up. And also this one. Those are the ones I see students mess up all the time. So it takes a record player 12 seconds to reach its regular speed. At its regular speed, it takes 31 seconds to rotate once. I have two numbers that are in seconds. These could be T or delta T. Which is which? Or are they both the same? Michael says 12 seconds is delta T. 31 seconds is T. Correct. So if I asked you, what is alpha? Right. The key here is that you only use T to get omega. That is literally the only thing you use it for. You never use it in kinematics. So you say, okay, my T is 31 seconds. So that means my omega is it does a 2 pi revolution in 31 seconds. So that is 0.2 radians per second. And then to get alpha, I do kinematics. This is 0.2, this is 0, this is what I'm looking for, delta T is 12. If I want to find out how far it traveled, I would do 1/2 alpha delta T squared is delta theta. That would tell you how many rotations it did while it was speeding up. Or this would be radians traveled while speeding up. Right? These are all delta T. None of them are capital T. You are done with capital T. Toss it away. Something at the height of this desk is really bad for my wrists. How's that feeling? Got any other questions? Okay, good. For circular motion, the biggest problem is misidentifying variables and plugging them in the wrong places. So that's what gets you every time. All right. Thanks, Shannon. Good luck. New person appeared. Don't have any questions about stuff. Banks, orbits, and loops. Okay. So orbits are easy, so I'll start there. By loops, do you mean like vertical loops? So Christian asked, omega only works in the equations if it's in radians per second. That's a really good question. And I hesitate to say yes, because it's more about the units have to be consistent. So for example, you don't want to have alpha in RPM and omega in radians, or the other way around. But you could hypothetically do like 1/2 alpha t squared plus omega t plus theta initial equals theta final, and then have, okay, this is -2 revolutions per minute, and this is 2 minutes, and this is 20 revolutions per minute squared, and this is 2 minutes, right? Like you can do that, but it sucks. It's really easy to mess up because you have to have everything in these kind of weird, right, minute squared, kind of weird units. So anything that has R in it, then everything else has to be in radians. So I recommend doing radians anyway, because sometimes you have to, so you may as well get in the habit of doing it all the time. Makes it a little more foolproof. But the answer is technically no. Like technically you can do whatever units are consistent. Okay. Orbits. So orbits are falling. So why are they falling? They're falling because gravity is pulling on them. And they are falling exactly enough that this provides exactly the right amount of acceleration to keep it in a circular path, right? So the m's will cancel, which is lucky for us, because if they didn't, it would be hard to go to space. And your AC, so you can write this as v squared over r, or as r omega squared. So basically, the idea here is gm over r cubed, cube root is omega, gm over r square root is v. So basically, to have a certain period, right, in order for the moon to go around with 28 days in a month, then there is a certain value of r. There's a certain distance away the moon has to be in that orbit. Right? And the same idea kind of over here, to have a certain speed. So this is for things like you're trying to launch a satellite, and it can have some certain amount of speed as it reaches its, right? So you launch it, like it'll have some speed. There is some, I don't know what that is, some radius r that corresponds to being able to maintain an orbit at that speed. Equivalently, these are both related to the mass of the bigger object. If they're about the same size, it becomes a little more complicated. So we don't do that. We just do when one of them is way bigger than the other, because they end up rotating the center of mass, and it ends up being like about torque and rotational kinetic energy, and it sucks. So we're not going to do that. So this is like how we know the mass of the sun, is because we know the Earth's period and distance, so we know what mass the sun has to have in order for that to be a stable orbit for the Earth. So the other thing you will see, this applies in general, not just orbits. So if you jump up, right, you feel some force pulling you down, it is actually this same GMM over R squared. So your G value is GM over R squared, where R is usually the radius of the Earth. So that means you can substitute here and end up with, which is something that you see on a lot of the equation sheets. I think it's on your formula sheet. The thing to remember that this is at the Earth's surface, because that's the only place G is 9.8. So this works for things like a car on a hill, or like a roller coaster, right? If the car is traveling with that critical speed, you could erase part of the ground and it would sort of Dukes of Hazzard jump over, because the force of gravity is precisely enough to keep it in that circular path. Critical speed. But it doesn't work in space because 9.8 isn't true. In space, you have to use the full version. So this is how you find out that like G at the level of the International Space Station is 8.9, not 9.8, but not also not 0. So if you were to suddenly like I don't know, lose all of your orbital velocity and like fall straight down, that's the acceleration you would have. If something like spontaneously appeared in space at that height, that's the acceleration it would have as it falls. Although as it gets closer, this would get bigger. It would fall back. So, Michael, is that helpful? Awesome. Let's talk about, so you asked about banks and vertical loops. Let's talk about vertical loops because they're connected. So you have this like this car going over a hill, right? At any given point, the forces are going to be normal force and gravity, normal force and gravity, normal force and gravity, presuming it's a circle, which most hills are not perfect circles. But the idea is that at all of these moments, you have an inward acceleration, and the net force has to equal the mass times that inward acceleration. Things moving in a circle are always accelerating. So right here, your normal minus gravity has to equal your mass times acceleration, which is usually, in this case, it would be downward. So this would be a negative number. There is a value where those two become equal, right? Where you have no normal force, where you're Dukes of Hazzarding it over this gap. Where I don't require the ground to hold me up anymore. So mg equals mv squared over r, m's cancel, rg. Hey, it's our same equation. It's sort of like an orbit, but you're not orbiting the center of this hill. That's weird. This r would be the radius of the hill. I mean, you kind of are orbiting the center of the hill. And this would be your 9.8. So this is the idea of your critical speed. And so generally for any loop, you have your net force is equal to mass times acceleration. For a vertical loop, you have to consider gravity, right? So if you think about like a Ferris wheel, and you're sitting in the car, right? What are the forces acting on you? Well, at every moment, you have a normal force and gravity. Normal force and gravity. You have a normal force and gravity. You have a normal force and gravity. Down here and up here, your centripetal acceleration is purely vertical. So you can set up this type of equation. So if you are accelerating downward, you have a lower normal force, so you feel lighter. If you're accelerating upwards, you have a higher normal force, so you feel heavier. What's happening at the sides? There has to be some force holding you in. So possibly it's friction. Or one possibility is that you slide, if there's no friction, you slide to the edge, and then it's normal force holding you in. Like a teacup ride. You smushed against the side. So you can also have things like swinging a bucket over your head. Right? So there was a conceptual question about this on the third test. So you have, in all of these cases, you have tension, which is inward, and you have gravity. In this case, tension is inward, gravity. So in this case, it would be tension minus gravity is MAC. In this case, it would just be tension because gravity doesn't matter. In this case, and it would be the normal force of the bottom of the bucket that's holding it up, right? You would have tension, gravity. Now tension and gravity are pulling down. So if you've ever swung something on a string, you realize you don't actually have to pull that hard at the top, right? It just kind of does it on its own. Well, if it does it on its own, what's happening is your V is RG, tension is 0. That's your critical speed. That's when it'll keep going, even if you are not actually pulling on the string. If you go faster than that, you do have to pull on the string or it'll fly away. So the question is, why doesn't it fall down? The answer is it is falling down. It is accelerating downward. But it is accelerating downward at precisely the right rate. Like if you throw a baseball, right? But if you're throwing a baseball over a house, it looks like the baseball is not moving towards the roof of the house, but it is. It's just because the house is curved, you can't tell. Does that make any sense at all? Why doesn't the water fall out? The answer is it does. It does. It's just moving. The bucket falls with it. And it's moving sideways fast enough that it doesn't, like, if you swing it too slowly, it'll fall on your head, right? But you're swinging it fast enough that by the time it falls, it's into that other part of the circle. That. But there we go. That makes a little more sense. The bucket falls with it. It's enough to go in circle instead of straight down. Why do you feel heavier at certain points? Because at this point, the Ferris wheel is not only having to stop you from falling, it also has to make you accelerate upward, right? It's the difference between, like, an object falls and you just catch it versus an object falls and you throw it back up, right? So the Ferris wheel is not just catching you, it's catching you and throw you back up. So it takes more force to do that. In order to have an upward acceleration, your normal force has to be greater than gravity. Does that make sense? It's not technically correct because when you're catching it, you're also making it accelerate upward, but it's like thinking of it in that way. Yeah. Yay. And it's 12:59. So it looks like Tomas appeared and hasn't asked any questions. I don't know if Tomas has any questions. If not, I might stop there because I'm starting to lose my voice a little bit. But I will be around for email, absolutely. Anybody on Twitch also? I can, like, cut this stuff out and make little things. Yes, you feel heavier at the bottom and lighter at the top. And if the Ferris wheel's not moving very fast, it's not very noticeable. But if it's moving really fast, it's really noticeable. Okay. Haven't heard anything from other people. So good luck. Happy studying. Email me if you have any more questions. Do great. Please do great.